Alright,
You have Band-Aids?
I do.
Can I have one?
I'm recording this, but sure.
That's okay. My finger on you.
Just happen to have this thing as medical supplies.
That's so you.
Here you go. Do you like Neosporin or anything?
It's probably fine.
Or
Okay, so what were we doing earlier in the week? Derivatives. Any questions on derivatives? Remember, the formula is
Not yet.
f prime of a is equal to the limit as h goes to 0. Okay, f of a plus h minus f of a divided by b. Okay. So remember, the whole concept is if you have a function f of x, basically what's happening here is you're picking a point that's close to x equals a, and we're calling it a plus h, x equals a plus h, and then we're calculating the slope of that secant line, which is what this stuff over here is. That's just the slope of the secant line. And the slope of that secant line is an approximation of the slope of this tangent line. But if you keep getting closer and closer and closer, then you get closer and closer and closer to the actual slope of the tangent line, which is what you're looking for, and that's what limits are. Okay? So that's the graphical representation of what you're actually doing when you calculate derivatives using that formula. Okay? Today, we're going to talk about just looking at a graph and identifying special points on a graph. Okay? So in particular, it's horizontal and vertical tangent lines. Okay? So first, let's talk about horizontal tangent lines. Horizontal tangent lines, first of all, occur. Thanks. Horizontal tangent lines occur when the derivative is 0, obviously, because if the tangent line is horizontal, horizontal lines have 0 slope, right? So horizontal tangent lines occur when f prime of a equals 0. Okay? Now, graphically, what that might look like, there's a couple different options. Graphically, f prime a equals 0 if there's really 3 options. First of all, f of a is a relative maximum, which just means that it's the highest point in its little neighborhood of points. The relative maximum. Okay, so graphically what that would look like is it's just a high spot on the graph. Okay, maybe it's something like this, and this is a relative maximum. Even though it's not the highest point in the entire function, it's the highest point in its little neighborhood of points. And you can see that the tangent line would definitely be horizontal at that point. This is also a relative maximum. And this also happens to be the absolute maximum of the entire function, but nonetheless, it's a relative maximum. Okay? What do you think the second graphical scenario would be? Yeah, relative minimum. F of A is, what did you say?
I'm stupid.
No, maybe you were right. What did
No, I
you
didn't. No.
say? Okay. All right. It's a relative minimum. So that would be like low spots on a graph, right? So if I have a function that's something like this, this would be a relative minimum right here. Again, it's not the lowest spot on the entire graph, but it's the lowest spot in the nearby, the nearby points. Okay. So the third scenario at which f prime of A might be 0 would be just a spot where it happens to flatten out for a moment or longer. Okay, so f of A flattens out. So it might be just a brief flattening out, like for example, x cubed. If you picture the graph of x cubed, it flattens out just for a second and then continues on its way. Right at that spot right there, if you were to try and draw the line that best approximates that, if you zoom way in, it would be a horizontal line, right? That's what the tangent line is. It's the line that best approximates the function if you zoom way in. Okay? Now, it might be a prolonged flattening out. That's not a max or a min. Also, like, it might be a function that's going along and then it just gets horizontal for a really long time and then goes down. It's not a max or a min, but still, like at this point, for example, the tangent line would be horizontal. That's the line segment or the line that best approximates that function really close up. Yeah, that's a great observation. Yeah, I mean, if I said if I define tangent line as like we did with circles, where we said a tangent line to a circle is a line that intersects the circle exactly once, that's accurate, because if you think about it, any other line, if it crossed through the circle like at an angle like this, it would have to cross through the circle again, right? So so that's an accurate definition when it came to circles in geometry. But when you're talking about this, we don't want it to be a line that just intersects at once, because then this might be considered a tangent line, which makes no sense, right? That's not what we think of tangent lines as being, just an intersecting line. So instead, when you get a little more sophisticated like this, a tangent line is a line that best approximates the function up really close. And it sort of fits our definition when you're thinking of this situation. It kind of fits the same definition as circles. But still, this line intersects the function more than once. It intersects it over there too, right? So that original definition, kind of toss it out the window and think instead in terms of like approximating the function on a really local linear level. Like you zoom in on a curvy function, it looks like straight. It's that line is the tangent line. Okay? It's a great question. All right, so those are the three situations at which the derivative is 0. Okay? So if they gave you a graph and they just said, identify all the points where the derivative is 0, you just find high spots, low spots, and then other flat spots. Okay? And it's that simple. So the next thing then that might occur is that the derivative might be undefined. Okay? If the derivative is undefined, at x equals a, then, and I just realized in my notes, we should make this really clear. It's this or this or this. It doesn't have to be all three of them. It kind of makes it look like I'm saying it's all three of them. So I just want to make sure this is really clear that it's this or it's It's a max or a min, or it could be some other flat spot. Okay. Okay. So if the derivative is undefined, well, think about what that means. There's a couple different possibilities. One possibility is that there isn't a tangent line. The function can't be approximated by a line at that point. So that's one possibility. The first possibility is there is no tangent line. No tangent line. Or it's not unique. Okay, there's no tangent line or it's not unique. So in other words, like if you think about all the different scenarios where this might occur, one possibility is maybe the function has a corner, right? Like a sharp corner. It's not like nice and smooth, but it has corners. Like, for example, the absolute value function. If you look at the absolute value function, it's V-shaped, right? And right at that point at the bottom of the V shape, if you tried to come up with a line that approximates that function at that point, no matter how small the neighborhood is that you go around there or how much you blow this up, it's still going to look like a corner. It's never going to look linear, no matter how much you zoom in. Does everybody agree with that? It's not like a smooth curve where you can zoom in and it looks straight. This is like a really abrupt change in slope. So there's no way that you can zoom in on this and it looks linear. So we say here, like the tangent line is not unique. Like I could draw, maybe we might consider this to be a tangent line because it just touches the function at a single point or whatever. But if you zoom in on that, it doesn't look like the function at all. The function is V-shaped and this line is not. So you can think of lots of these things as being kind of like tangent lines if you think of it in a really elementary way, but none of them are actually approximating the function at that point. Okay. Another possibility is maybe the function has some sort of discontinuity. Like maybe the function is going along. So I'm just going to write for any discontinuity. So maybe the function's going along and there's a jump. Like the function's going like this, and then it jumps down to here. I mean, if I zoom in to this section of the graph, there's no way I could draw a single line that approximates the function at that x value. It's impossible, right? Because part of it's up here and part of it's down there. There's no line that's going to approximate that whole thing, right? It's never going to look like a line, no matter how much I zoom in on that x value, okay? Now maybe it'll look like a ray up here and a ray down there, but that's, again, that's not a line. They might have different slopes or whatever, right? So it's not unique. So that's one type of discontinuity. Another type of discontinuity is a hole, right? So maybe the function's going along, it's missing a point, and it's going along, right? Again, if I zoom in on that point, it's going to look like a line on one side or a ray on one side and a ray on the other side, but it's never going to look like a line because there's always going to be that gap in it, right? So this one, it's a little weird because you could say, well, really, I mean, it kind of continues on in the same sort of direction, same slope or whatever, but still, the function cannot be approximated by a line because there's a hole in it. So same thing, the tangent, the derivative is undefined at that point. And then the third situation, what's the third type of discontinuity? Yeah, a vertical asymptote.
Yeah.
So if you have a vertical asymptote, same thing. There's a discontinuity there. The function is never going to look like a line if you zoom in on that spot. Regardless of how much you zoom in on that spot, it's never going to look linear. Okay? So this is called a corner. Another word for that is actually called a cusp. So that word in math, cusp, technically is the intersection of two curves, and a corner is the intersection of two lines or rays. But if you called that a corner, no matter what, everyone would know what you're talking about. But if you ever see this word cusp, that's what it means. It's just like a sharp edge on a graph. Like, for example, it might just be like something like this. That's a cusp. But it's the same scenario, right? So that's what that is. Okay, so that's one possibility if the derivative is undefined. It might be that there's no tangent line, or it's not unique. Another possibility is the tangent line is actually a line that has undefined slope. What type of line is that? Vertical line. Maybe the tangent line is vertical. That's possible, right? So the second scenario is that tangent line at x equals a is vertical. So we've actually seen functions that have this situation happening. In particular, the graph of x cubed looks like this. All right, so if you picture the graph of x cubed, I'm not going to draw the axes, but it looks like this, roughly. It goes like that. All right, it's still a function. This function passes the vertical line test. However, right at that spot right there, the line that best approximates this function would be a vertical line. Right? So that's possible. And still, the derivative would be undefined. Not because the tangent line doesn't exist, not because the tangent line is not unique, but because the tangent line is vertical. Okay? So if you saw a graph, you should be able to identify points where the derivative is 0, high spots, low spots, flat spots, points where the derivative is undefined because there is no tangent line, corners, cusps, and discontinuities, and points where the derivative is undefined because there's a vertical tangent, points that look like that, okay? So let me just show you what these problems look like on Delta Math. They're super easy. All you have to do is identify points where the derivative is 0, identify points where the tangent line is vertical. Okay, so let me just show you. So here's the assignment. So in this question, it's just, they give you a little random squiggle graph, and it says, determine all values of x where f has a vertical tangent line. So it's just a single point in this case. It's just that spot right there. You can see that just for a moment, it goes vertical. So all they want to know is what's the x coordinate of that point. It's x equals 3. That's it. So that's what you type in, 3. Now, if there happen to be more than one, remember you use this plus button here to create more answer boxes. But here it's just x equals 3. Okay. Other questions they might ask, this one's a vertical tangent. In this case, there's also just one. Hang on a second. This one says horizontal. So there might be lots of ones. Like in this case, there's many answers. There's a horizontal tangent here because there's a max. Not here. Here, the derivative is not defined because there's a corner there, right? Or a cusp. So it would be at -6. There's another relative maximum right there at -1. This is a spot where it just flattens out for a second. That doesn't look like a corner to me. It's a little close, but I don't think that they intended for that to be a corner. So you'd say 1 is another point. And then here's a relative min at 6. So this one would have 4 different answers that you type in. Okay? If they gave you this problem and they said, where's the vertical tangent, it's just 1 point right here. But you just have to identify whether they're horizontal. If it's horizontal, maxes, mins, and flat spots. And if it's vertical, just spots like this where it goes vertical. And they're actually not going to ask you about where it's undefined for other reasons, but you should definitely know that just because, I mean, you should know that there's graphically other situations where the derivative might be undefined. Okay? Any questions about that? So on this one, you'd have to scroll down you press like the plus thing to get 4 answers, and then just type each of them in. Any questions? All right, that's it.
On the homework thing, it says that, like, there's 2 assignments for the same.
Yeah, I don't understand that. I don't know why that's doing that.
So we don't have.
Just do one of them. Yeah, I don't know why, that's really strange to me.
Because I have like.
Is this the first week that that's happened?
Yeah. But I have social tangent lines for social tangent lines and then social tangent lines for derivative slash social tangent.
I don't understand why that would be. I don't know. I'll do some more research here.
They're
But
for the same thing.
yeah, just do one of them. It should be the exact same assignment, right? I
Yeah,
think
there's 2 social tangent lines and one says derivative slash.
that's really weird. All right, yeah, just do one.